Well, hello and welcome everybody. So our only announcements for today are, let's go through those quickly. There's an M in there somewhere. Just another reminder, final exam is Monday, May 4th, 9 to noon in the morning. Other things are you have your quiz due today, quiz 10. I think at some point I might have said quiz 9 accidentally, but it's quiz 10. So that's due tonight at 5 p.m. You have one homework left to do. That's due on Wednesday. And that's on section 5.1, but I just want to remind you, section 5.1 is not on the exam, if that's any consolation, because we're doing it so late. Not on the exam. Let's just try that again. Okay, and along the same lines, when we're talking about homework, because I offered this to one person, I feel I should offer it to everybody. So if so what I've decided is, while you're studying, if there were a couple homeworks that you didn't quite complete or would have liked to have done more work on, I'll let you pick up to 2, and you can email them to me, and I'll give you an extension on them. The only caveat is any new work you do will be worth not quite the full amount. It'll be worth 90% instead of 100. Okay, so if that's something you think you would like, just send me an email. You can choose up to 2 of your past homeworks to keep working on. Okay, so other than that, do you guys have questions before we get started? Maybe it's worth briefly talking about the final exam. So the final exam is not written entirely by me. It's written by basically all the professors that are teaching Calculus 1 right now have input. So, that's a warning to not think that every problem on the exam will look like exactly like something I've given you. So that may change your study strategy a little bit. You want to concentrate a little bit more on like overall, big picture ideas. Make sure you can do the basic computations as well. But yeah, just a heads up. Though they're all of a very similar difficulty level, I would say. Just the phrasing might not be exactly what you're expecting, though I've changed a lot of that so that it's more like what we've done. Okay, so I thought we'd start today with a little bit of review, just to throw in some review problems while we're at it, because we only got a couple days of class left, so we're going to squeeze some in today and on Wednesday. So let's look at this example. This one's from way back when. Okay, so this function gives us, or I mean, this question gives us a function, which is piecewise, and it asks us to figure out what this particular constant can be. So we imagine we can change the number c around, and which of them would make it constant, or which of them would make it continuous. And whenever we say continuous, remember that means continuous everywhere, unless we say continuous at a point. So the way I would approach this is, kind of what's going on here is maybe we don't know exactly what this graph looks like. And I don't quite know exactly what it looks like off the top of my head. But what I do know is, I know the function does something, and then at 0, it does something else, right? So at 0, there could possibly be a hole here. And then at 0, if x equals 0, it's just the value c. So c could be somewhere else. And then the function could continue on doing something else. Right, and so the question is asking where this is continuous. And so the first observation is if you look at this first part of the function, the sign, it's awkward to keep all this on the screen at once, but the observation is that based on what we talked about continuity, is if you just take the basic functions, oops, that's not the right thing, and you put them together using like the operations of composition, multiplication, division, addition, that they are continuous on their domain. So this part itself is continuous on its domain, and its domain is everywhere that the denominator is not 0. That's the only thing that could go wrong here. So its domain would be everything but 0. Okay, so our original function was that function if it wasn't 0, right? So that's saying that our entire f is, so this tells us that this function is continuous at least on that part. And the only place we then have to worry about is what happens at 0. How do we fix it? Like, which value of c do I choose? Because I can choose c by moving it up or down to be a bigger or smaller number. Which number should I choose so that becomes continuous, right? So we have to figure out what this value is, right? Because that's the one that will make it continuous. Okay, so that leads to the second observation, which is basically, if you remember, what's the definition of continuity? So the definition of continuity says f is continuous at 0, right? Because we know it's continuous everywhere but 0, so we just want to make it continuous at 0 as well. That means that it has to have this equality, right? The limit, when you take the limit at the at that value, 0, it has to be the same as plugging in to your function, right? That was the definition of continuity. Okay, so then we ask ourselves, well, so what's f of 0? Well, if you look here, it says if x is 0, then your output is c. So the right-hand side here is just c. And the left-hand side, well, remember, what is a two-sided limit really asking it's for? It's like saying, suppose I forget what happens at 0. What does the function nearby tell me what the value at 0 should be? What should I fill it in with? And so, let's see. So everywhere except at 0, the function is this sign thing, right? Because a limit doesn't care about what happens at 0, it just cares about what happens nearby. Plus x squared over x. Okay, so in order for this to be continuous, we have to make sure that the c value we choose is whatever this limit is. Okay, so we've kind of reduced the problem to now just figuring out what this limit is. Okay, and that's sort of an exercise in itself. So recall, we learned this limit that's not all that obvious, that if I take the limit of sine x over x as x approaches 0, you know, this only works when x goes to 0. It doesn't work at like infinity or another number. So this turns out to be exactly 1. Okay, so the trick here is how do we use this? How do we use this? Whoops. How do we use this? Yeah, you guys get the idea. How do we get that to, how do we use that in this formula here? And if you think back to what we used to do, the idea is whenever you have something inside of a sign and you think you have to use this particular trig limit, you want to make the same thing appear in the denominator as whatever's in the sign, right? So this part here is really, like if you factor in an x out, what would be left is 3 plus x, right? If you factor that inside. Why do I keep writing that? Okay, so that means the thing we would need to add to the bottom is a 3 plus x. But we can't just go adding things without changing the limits, so we have to really multiply by 3 plus x over 3 plus x. Okay, and so yeah, if we do that, this limit becomes we have this part, and then the leftover part is 3 plus x. And we can even break that into two separate limits if we wanted, right? We can put the limit on the second bit, assuming it has a limit, which it does. Okay. And so now the only thing we have to verify in this first limit is as x approaches 0, so does 3x plus x squared. And really vice versa. So that means this entire limit is essentially this one. So this one's going to go to 1. And this one's going to go to 3 plus 0. So putting it all together, we have 1 times 3 plus 0 is equal to c. So c is 3. Okay. So I kind of like this question because it has a lot of important ideas in here. But remember, the basic idea here was you try to analyze where the function was continuous and figure out where it could possibly be not continuous. The only place it could possibly have not been continuous is at 0. And we could fix it by choosing the right value of c. And the definition of continuity says the limit of the function has to equal the value we get by plugging in. And so that gave us a formula that let us solve for c, essentially. Okay, so questions about this one? Okay, well, let's do one more, and then we'll jump into section 5.1. Or maybe we should just jump directly into 5.1 and then do anything extra at the end of class. So let's jump right into. So section 5.1 is essentially what we're doing is we're trying to find areas between curves. Okay. And it all comes down to one essential idea. And that idea is this. Okay, so the idea is, so in this section, we're going to be almost exclusively interested in calculating positive areas. So in the past, when we've said the word area related to like integrals or antiderivatives, it's meant signed area, where if it's below the x-axis, you count it as negative. Here, we're going to be talking about positive areas, unless you're told otherwise. And so the idea is if you have two functions, f and g, and you know f is the bigger one, then the area between them is given by this integral. And it's pretty easy to see why that is if you draw a picture. Right, so if you have two functions and f is the bigger one, which means it's on top, right? So f might be up here. Then you might have a g down here somewhere. And then we have some interval here. Then the area between them the area between f and g So the area we're interested in would be, it's a good color for that, this maybe, would be this area here. So that's what we're trying to calculate, is that area in there between them. And if you think about it, you know, this integral, you could write this integral as two integrals, right? Right, there was this property that lets us split it up. And so the first integral, maybe that's not a good color to do it in. The second integral would be this area here, right? The area under g, or between g and the x-axis. And the first integral here would be this entire thing, right? So it's saying if we want just the light blue part, this top, you know, this part in here, if we want to get just that, one thing we can do is we can take the complete area under F, the yellow part, but we don't want all of it. We get rid of the part in pink, right? So we're taking the complete yellow minus the pink, and all that's left is the light blue. And that's basically what all this formula says, right? So if you think about it in terms of areas, it's not too bad. Okay, so this does have the condition that F is always bigger. So in general, there's like a slightly more general version. So in general, so if you don't want to worry about which function's on top, one thing you could do is you can just always put absolute values here. But this is also sort of helps with another case, which, you know, if you think about it, maybe you had a picture like this. Maybe you had your F looked like this, and your G maybe looked like this. So maybe they crossed. And maybe your interval contains the crossing. Then the area that this would calculate would be this area, and we'd count that as positive, and then this area we would count as positive. Okay. So in general, like whenever there's a switch, if you just put absolute values around it, that's technically correct. But if you think about what we were talking about on Friday, really what you would have to do to actually calculate that is you'd have to split this integral into two integrals at C. You'd have an integral from A to C, and then one from C to B. But yeah, it's technically the same as the absolute value. So this is sort of the most general formula. This one always works. That's just sometimes a little harder to work with. Okay. Oh, where did my check? Okay, so let's try one of these with an actual function and some numbers. Okay, so here we're asked to find the area enclosed. So that's, when you read math, you have to be very careful to like the words people use. Because everything, math is very concise, so we typically mean what we say, at least most of the time, unless we make a mistake. And here, you notice I didn't give you any bounds, right? So we have to figure out our bounds, and that's why this word enclosed is important. Because if you think about it here, well, maybe one thing you could do is you could notice that the first function, you could factor this as x times what? 5 minus x. So that goes through 0 at 0 and positive 5. And it's in downward facing parabola, so who knows what it does, but it does something like this. Oops. And then our other function is just a line, y equals x. So maybe somewhere in here. So this will be y equals x. This one is y equals 5x minus x squared. And so the area that's enclosed here, enclosed means that the functions are the sides of the area. It means on every side of that area, there should be the function. Okay, so we're really talking about this area. So that means the interval we're looking for will be whatever these x values are. So this one we don't quite know yet. This one is clearly 0. So we know our a will be 0, but we don't know what our right-hand endpoint is. And so how do we find where these two functions intersect? What do I do? What do you guys think? What equation can I write down that will tell me where these two things intersect? Well, the answer is whenever you're trying to find, this is a point, whenever you're trying to find a point that satisfies two equations, you have to somehow use both pieces of information. And basically what you do is you plug one in for the other. A lot of people like to say that you set them equal. I don't think that's quite the proper way to say it. I think it's better that you plug, y, you're substituting x in for y in the first one. So maybe something you would do is you'd take x equals 5x minus x squared. Well, that's the equation you end up. This should tell you all the points, all the x values at least, where the two functions have the same outputs. And if we do a little work here, what do we get? Let's move everything to like one side. X squared minus 4x is 0. I moved everything to the left. So if we factor that, we would get x times x minus 4. And that gives me two solutions, x equals 0 and x equals 4. Which in our picture makes sense, right? We expected to get the 0 because we knew they intersected there. So that means this point here is 4. Okay, and now to calculate the actual area between these things, well, we're going to do an integral from 0 to 4 because that's the x. So whenever you're doing an integral with an area, kind of what you should imagine is if you take a horizontal line, like if you're starting to if you have a vertical line at 0, and you sweep it to the right, everywhere that vertical line is hitting your area should be included in your integral, right? So, if I sweep from 0 to 4, I'll cover the whole area. That's the idea. But now, what do you put in the integral? There's kind of two options. You could put like x minus, or you could put it the other way. And, well, here, if I was being very specific, and maybe I should be the first time, we really mean positive area. So we're looking for positive. And if we want a positive number to come out, we better have the top function come first, right? Because we want to have the bigger minus the smaller. So the correct thing would be to have the 5x minus x squared, because that's the top function. Right? So this goes all back to this very original idea that if you have one function bigger than the other, you put the bigger function first, right? And subtract off the smaller one. Okay, so now you have an integral. Now you can forget all the pictures and stuff and just crank through the integral. Maybe you simplify a little bit first. Take an antiderivative. Plug in. Okay, so you just get some number here, right? And this number is our area. Okay, so this sort of illustrates the basic ideas here. A lot of times it is very useful to have a picture, and the main use for the picture is, I guess there's a couple reasons. One is you want to be able to tell like what's your range of x values. Often the picture isn't quite good enough for that. You have to do some sort of solving to get the exact value. But the other thing is to tell which function's on top, right? Because we knew the red one was on top, so that told us which one to put first. Okay. And then, yeah, you always just write down the integral of the x values over which the area lies of the bigger function minus the smaller function. And if it switches which one is bigger or smaller, then you have to split the integral into pieces. Okay, let's try another one. Okay, so here, we're not just given two functions. We're actually kind of given four, though, we're given four equations. Two of them aren't actually functions, the x equals ones. And so here we have to figure out what area is even being asked for before we can start to compute anything. So we have to draw a picture. So let's draw a quick picture. So we have x plus 1. Let's throw x plus 1 in there. Maybe that's something like this. Then we have this. So this value is 1. And then we have our parabola. So that one starts up at 9 and is downward facing. So it's going to do something, who knows exactly what. Something like this. And then we have these two x values. So there's a slight issue when you're drawing here. So what does x equals minus 1 look like? Well, if 1 was here, or sorry, minus 1 was here, then it would be a vertical line, right? Because it's all the points that have that particular x value, and y could be anything. Okay, but there's a small issue that if you don't think about it, you might not know where to draw this minus 1. Like, is minus, there's these intersection points here. And is minus 1 in here? Or is minus 1 out here? And that's something worth checking. So if we did try to figure out whoops, what happened here? Well, sort of. So on that side, one obvious way to figure out which it is to notice that where is this parabola 0? And that's at minus 3. So the minus 1 obviously has to be to the right of that. So minus 1 is in here somewhere. And if you think about it, it's exactly here. Right? Because if I plug minus 1 into y equals x plus 1, you get 0, right? On the other side, the x equals 2, you might not be, you might not be sure, is 2 over here somewhere, or is 2 over here somewhere, or is 2 over here somewhere. And to decide that, you kind of have to, whoops. What did I delete? To decide that, the one thing you could observe is that this is 3, because this one over here was minus 3. So 2 definitely has to be the left of that, but then you might not be sure, is it in here or is it in here? Because the pictures are different in those two cases. So to figure that out, you want to figure out what is this value. And we get that before. We're trying to find where the red line intersects the yellow line. So we set those, so we plug one into the other. And try to solve. So we get x squared plus x minus 8. Does that factor? Not nicely. So then you would resort to like the quadratic formula. You'd get something like this. So you get negative 1/2 plus or minus square root of 33 over 2. And you could either use a calculator or you could just observe that, you could compare this to square root of 36. So that's bigger, and that would be 6. So this is bigger than 3, right? And so minus 1/2 plus something that's bigger than 3 will be bigger than 2, right? So that means in our picture, That 2 should be in here. Should be to the left of this intersection. And so the area then we're trying to calculate is this area. Okay? Because that's the one, when we say the word enclosed, what we mean is that it's the area which has these 4 functions as its sides, in some sense. You kind of have to figure out in what manner that happens. And so, yeah, but once you know this picture, then it's pretty clear that the x values that are under my area, and if you take any point in here, go from -1 to 2, which, probably would have been my first guess anyways, looking at these. But it's good to check that something weird isn't happening. Because if 2 had been over here, then I would have had an extra area here, and I would have had to do 2 separate integrals. We'll do one like that in a minute. But in this case, you just and now the one on top is the parabola, top function minus bottom function, and then crank through it. Okay, so you do something, simplify maybe. So this is minus x squared minus x plus 8. From -1 to 2. So take antiderivative and then plug in. -8/3. So you get that, and then you plug in -1. So then you get +1/3, -1/2, -8. And whatever that works out to be. I guess we could try to work it out. So 16 minus 8 is 8. This is the same as 2 minus 2 plus 2/3 minus 1/3 plus 1/2. So that's what, 4 minus 2/3 plus 1/3 plus 1/2. So basically, the only reason I'm doing this is to check that we got a positive number. That's something that can be worth doing, right? Because we expected a positive answer, right? And so this is 4 plus 1/3 minus. Like, I don't even have to simplify it all the way down. Now I can easily see that this has to be a positive number, right? So if I start with 4, add a 1/3 and subtract 1/2, I'm still going to be way bigger than 0. Okay. So yeah, for a lot of these problems, it's basically just draw the picture and then take the integral over the x values that lie under your area of the top function minus the bottom function. All right, so questions about that one? Okay, let's try another one. Okay, so here, you may be tempted to go writing down the integral, but it really does pay off to have an idea what the picture looks like. And so here the picture, if we try to draw some sine and cosine functions, let's see, sine looks something like this. Cosine starts up at 1 and should hit 0 here. Whoops, let's make that a little better. It should go like this. And then peak down here. Something like this. So this is cosine of x. This is sine of x. And then where is pi over 2 here? So we know where 0 is. 0 is here. Pi over 2 is when cosine is 0. And sine is 1, right? Okay, so if we look at this part then, the area we're interested in is the area between these curves, the positive area. So what we really mean is we mean this area here plus this area here. But the issue here is that which function is on top changes over this interval, right? So I mean, you could go ahead and just write down this integral, right? I mean, and this is what I mean. You can always just write down this integral if you know the bounds at least. And it doesn't matter which one you put first, cosine or sine, because they're in an absolute value. But remember, when we're taking an integral of something that has an absolute value, you have to break it into the pieces wherever it's positive or negative. And to do that in these cases, the easiest way to do it is to figure out in our picture, where is this intersection point? And then we'll do one integral on this piece where the yellow line's on top minus the red line. And then over the second bit, we'll do another integral from whatever the middle is to pi over 2 of red minus yellow, right? Top minus bottom. So you just split it into pieces wherever it switches. And yeah, so the thing we don't know is what this intersection point is. And we find that by setting them equal. So the point of intersection, I mean, there's many of them, but there'll be just one of them on 0 to pi over 2. If you plug one y in for the other, you get sine equals cosine. And I guess there's many ways of thinking about this. You could just think to yourself which angle x produces the same thing when you plug it into cosine as it does to plugging it into sine. Or you could divide it by cosine and get like 1 equals tan x. And if you think to yourself, like what angle has the same values of sine and cosine, which would make tangent 1? And the answer is just, well, pi over 4, then there's other ones, but what would the next one be? So negative pi over 4 doesn't even work. It would be 5 pi over 4. And there's a whole bunch more, right? But the only one we care about is the one that's between 0 and pi over 2. Okay, and so that tells us to actually do this integral. What we should do is we should do an integral from 0 to pi over 4. And in that region, so in this region here, maybe let's fill in our pi over 4. Over that region, the yellow one was on top, and the yellow one was cosine, right? We had cosine, and then we had sine. So yellow minus red will be cosine minus sine. Right, really what we're doing here is we're making sure that each of these integrals is completely positive. And then our second integral will go from pi over 4 to the end, pi over 2. And during that region, you know, in this region, the red one was on top, right? Red was bigger than yellow. And so we would put it in the reverse order, sine of x minus cosine of x. Okay, and then you crank through these integrals. So the integral of the first one would be, let's see, sine of x plus cosine of x from 0 to pi over 4, plus then the second integral will be minus cosine of x minus sine of x from pi over 4 to pi over 2. Plug everything in. So sine of pi over 4 is root 2 over 2, root 2 over 2 for cosine as well. 0 will be 0 plus 1. Cosine of 0 is 1. So this first term became this term. And then the second term will be minus root 2 over 2. Minus, or sorry, I wrote it backwards. So you should plug the top one in first. It should be minus cosine of pi over 2, which is 0, minus sine of pi over 2, which is 1. And then when I add minus root 2 over 2 minus. Okay, so you'd get something like this. So you get root 2 minus 1 minus plus negative 1 plus root 2. So it looks like you get 2 times square root of 2 minus 1, or sorry, minus 2, which is a positive number, right? Because root 2 is bigger than 1, so 2 times root 2 is bigger than 2. And so that minus 2 is positive still. Okay, you guys getting the hang of this a little? Okay, so there's one more example of this I want to do. That illustrates sort of a different way of thinking than we've sort of come across so far. All right, so this one looks a little different, primarily because, you know, we're used to things where it says y equals something, right? But this says x equals something, x equals 2y squared. And yeah, so you have to think a little bit about how you would draw this. So if you did switch the variables here, this would be like y, whoops, be y equals 2x squared, right? We know what that looks like. That looks like an upward facing parabola that has its vertex at 0. So if we draw, but when we switch the variables, it means, we're treating, so really the important thing is to remember which way is positive, right? So on the x-axis, to the right is positive. So that means upward facing will mean open to the right. Whereas, normally upward facing would be open upward. And so the way I think about it is I know the vertex is at 0. And then I pretend the x-axis is the y-axis, kind of. If you kind of just tilt your head to the right, then this one really looks like this. It's like a parabola, but it's opening along the x-axis instead of the y-axis. But it's opening along the positive y-axis because it's x equals 2y squared, right? Another way of thinking about it would be which I find harder to think about when I'm actually graphing things, but it does work if you can really follow it through, is if you had the original graph of, y equals 2x squared, and you reflected it over the line y equals x, then you would get your graph, right? So we're saying if we folded this way over here, right, then you would end up with your graph. That's another way of saying it, is when you switch x and y, you're really folding over the line y equals x. But I find that kind of hard to think about unless it's very simple functions, which for parabola, it's fairly simple. Okay, so let's get rid of all that. But in the end, the graph of 2x equals 2y squared looks like this. And then if we look at the second one, it says x equals 4y squared. Well, that would be similar to y equals 4 plus x squared, which would be an upward-facing parabola that's shifted upward by 4. And so, upward on the y-axis translates to the right on the x-axis. So instead of going up, we go to the right by 4. And then it's still an upward-facing parabola, so it still opens in the positive x direction. But because of the 2, it's a little bit less steep. So it does something like this. So a little non-symmetrical, but whatever. Sorry, x equals 4 plus y squared. And I should do that in green. Okay, so now we have our two graphs. So the area that's enclosed by these are like bordered. The area that's bordered by them would be this area. And just applying the technique we've used so far, it's not quite going to work. Because if you think about it, in this region between here and here, so maybe I should mark this. This was 4. Oops. But in this yellow region here, well, the top function, at least the way we've been doing it, the top function was, the green function was on top, and then the other part of the green function was on the bottom. But when you go past there, right, because there's some area all the way up to wherever this is, right? So in this second region, then you could do like this function would be on top minus this function. But then you have another part down here where you would have like this function minus this function. So if you were to do it this way, well, let's leave that. You would end up with 4 regions. You'd have to do, 3 integrals. You'd have to do an area here, then an area here, then an area here. And that seems like a lot of work, but you could do it, right? But it turns out there's an easier way. Okay, so we just have to kind of shift our point of view a little bit. Okay, so if we go back to just looking at it this way, and if we think about now, instead of subtracting y values like we did before, we're going to subtract x values. So we're going to do it the other way. We're going to take this minus this. And we're going to, so like before we were thinking of if I had a vertical line and I sweep it to the right, that's going to give me like the area. Now I'm going to take a horizontal line and I'm going to sweep it upward. Okay, so the idea is we're kind of just changing x and y. Or well, not changing them, but we're kind of swapping the roles in which we use them. So instead of doing an integral in x, so remember, an integral in x would tell me the area under that function, or yeah, between that function and the x-axis. If I do an integral now in y, it would tell me the area between the function and the y-axis, right? So we're kind of, you can imagine turning this sideways. You can imagine like rotating this 90 degrees so that x was facing up, and that's essentially what we're doing. Though you have to be a little careful because when you do that, y positive is then to the left. But it's essentially what we're doing. I don't think I can actually make that happen on my screen very easily. But yeah, so if we do that, then to tell which one's on top, well, it's the blue one. Okay, so the one that's on top means which one has the more positive x value, which one is farther to the right. So instead of top, we have more to the right. So it'll be the blue one is on top. So we're going to do some sort of integral. Right, what am I writing? So 4 plus y squared, because we're doing a y integral, minus the green one, which is 2y squared. And then we have to worry about the bounds. And well, the smallest y bound is this one here. And to figure out what those are, we have to set them equal, or plug one to the other, rather. And what do we get? We get y squared equals 4 to y equals plus or minus 2. So this is minus 2 and this is 2. So it's sort of the same process, but you're just looking at things sideways. And sometimes that's easier, right? Now this is one integral instead of 3 integrals, and I don't have to find like 3 different bounds. But, you know, it is sort of conceptually more difficult. But once you get over that, it's easier. And then you crank out the integral. Which is 8 minus 8/3 minus negative 8 plus 8/3, which is what, 16 minus 16/3, whatever that is. some number, right? But it's a positive number, right? Because 16 over 3 is, that's what, 5 1/3, I guess. Okay, so questions about that one? That one, these tend to be the trickiest when you first see them. Just because of this change in perspective, it's hard to wrap your head around. But it is important to start getting to be a little bit flexible with like your notations and stuff and your perspectives. Okay, well, if you guys don't have any questions, I'll let you go. We'll be doing some review on Wednesday. But other than that, have a good day. And just a reminder, your quiz is due at 5 today.